All right, folks, welcome back. We left off last time talking about the apparent magnitude of stars and the magnitude, the scale that astronomers use. We talked about how they lined up into six different scales, and we also talked about how this just kind of gives something called the apparent visual magnitude. And we want to kind of, with modern technology, we can do more than that. Stars emit all kinds of different radiation, not just what humans can see. This scale, the distance to the Earth, is not taken into account. So there's a lot of stuff that goes into this. Just like if you were shining a flashlight from a large distance, the light does spread out. And this is not really taken into account by the apparent visual magnitude. It's great for observations. It's great for looking at and kind of giving a generic idea of how bright something is, but we want to get into it more scientifically. So scientifically, they use something called what we call flux. Now, flux is the amount of light energy that hits a square meter in 1 second. So a square meter of the sky, if you were looking up, square meter of the sky, how much light energy actually comes through that every second. And that's what we call flux. Astronomers use this to precisely measure the light energy that reaches the Earth from luminous celestial objects. How does this work? Well, the magnitude scale kind of lines up with the flux ratio. I know this kind of sounds kind of crazy, but there's a flux ratio, the amount of light that goes through. Astronomers can convert between magnitudes and brightness in terms of fluxes. If two stars have fluxes FA and FB there, you see there, and they differ by a magnitude of 5. All right, so one's a 1 and one's a 6, or a -1 and a 4. Excuse me. Their ratio of their fluxes is 100. So if magnitude difference of 5, their flux ratio is 100. So if two stars differ by 1 magnitude, they have a flux ratio equal to the 5th root of 100, or what is about 2.51 for every 1 magnitude difference. All right, so that just kind of works out. That's just the way that the math works out. As you can see on the screen, you see, if this was 5 or F flux ratio, flux of A and flux of star B, and they differ by 100, their flux is equal to 100. That's for a difference of 5 magnitudes. And what we would do is just take the 5th root of that number, and we would get 2.51 for the flux ratio of 100. This means that when compared to the light of a star of a particular magnitude, a star with a magnitude 1 greater will be 2.5 or 2.51 times brighter. That's all this really means. So it's a little bit of it's not really that complicated a math. It's just one ratio, take a square root or a 5th root. But what it really translates to is if I see a star that is a -1 magnitude, and then I see a star that is a 0 magnitude, I know that the -1 star is 2.5 times brighter than the other star. Two stars with a magnitude that differ by 2 will have a flux ratio of 2.51 times 2.51, or 2.51 squared, and it gets bigger and bigger and bigger from there. The difference in magnitudes and flux ratios. The amount of energy coming from the star, the brighter the star is, the greater that difference. So it changes to a scale that's a little bit different. We'll take a look at the next slide here. Magnitude differences and flux ratios. A magnitude difference of, if they're the same, obviously that difference is 1. They're the same, so they have the same light energy coming through. All right, the same flux. If they're 1 magnitude difference, 2.5 times, and then we got 2.5 times squared, 2.5 times cubed, and so on, to where we get the flux ratio, the amount of light energy hitting the difference in the flux between one star and the next star that's 5 greater is 100. So 100 times more light energy coming from a -4 star magnitude than a 1 star magnitude. All right, or a 0 and a 5, or so on and so forth. It's kind of a little bit confusing because the negatives are the brighter ones and the dimmer ones are the more positive numbers, where +4 is really what we use. All right, this means that when light of a star of a particular magnitude with a star of 1 greater will be 2.5 times brighter. 2 stars, 2 difference, 2.5 times squared. We kind of get that. That's what's going on. More on the magnitude differences as you go up and up and up. If they have 25 flux ratio difference, this would be like the sun and our brightest star Sirius, or our bright star Sirius. So the sun is like a negative 25. Sirius is like a negative 2. All right, so that's a 25 magnitude difference. The sun is 10, what is that? 10 billion times more light energy coming from the sun than coming from Sirius through the earth, which makes sense. The sun is super bright. There's a lot of energy coming from it. It tans our skin. It burns our skin. It's able to be converted into solar energy. It warms the planet. It's responsible for all kinds of different stuff. It grows. That energy is able to grow just about everything on the planet. If there was no sun, there would be barely any life. We need that energy from the sun. So that 10 billion times greater is definitely important. The formula for the flux ratio works out to be what you see here on the screen. This is that ratio. We got 2.51, and then we've raised it to whatever magnitude difference. Whatever the magnitude difference is. The example, if a magnitude difference is 6.32 magnitudes, what is the flux ratio? All you're going to do is, that's the difference right up there. You're going to plug that number in, and you get the flux ratio is 336. Is a difference of 336 times more light energy coming from that star A than star B. All right. Star A is 336 times larger than the flux from star B, and this is the amount of light energy hitting a square meter. Remember that. That's kind of how all of those were set up previously. If you look at these numbers here, you've got magnitude difference of 8 comes out here. If you did put 2.51 to the 8th power, you would get 1580. It means that a star with a magnitude difference of 8 is 1580 times brighter. Not brighter, back up. More light energy coming through. It doesn't necessarily translate to brightness. All right, the magnitudes do deal with brightness, but that's not a direct one-to-one. The formula for differences in magnitude, if you want to find out how much difference in magnitude, say that you know how much flux, this is what that equation works out to by doing a little bit of algebraic manipulation of this equation, moving it around to solve for MB minus MA. If you have time, I encourage you to try to go through that math if you're at that level. So if you're in like pre-calc or even algebra 2, well, I guess if you've taken algebra 2, you should be somewhat familiar with the logarithms. So any of you pre-calc students, if you want to try that out, try to get from here to here. All right, it's not as easy as you think. There's a couple of key points in there to make, but try that out if you have, if you're interested. I always thought those things were kind of fun to do, but the flux difference, if you know that, and you want to find out the magnitude difference, you can do it. For instance, the light from Sirius, which is pretty bright, has 24.2 times as much flux. It's 24.2 times brighter than the light from Polaris. What is their magnitude difference? And when I plug that in, I get 3.45. This means the difference in magnitude of the two stars is 3.45. Make sure that when you're doing this on the calculator, if you don't know already, the log right here is log base 10. On most calculators, it does that automatically. It assumes base 10. Just confirming that this is log base 10. All right, enough with the math. We're not going to deal with that a whole lot, but just those are the two equations. Those are two examples that you can pop back to if you have trouble on the homework or anything. The biggest thing, the most maybe important thing that we can do with all of this is you can start to learn to look at things and see how it's laid out, is this model of what we call the celestial sphere. All right, ancient astronomers believed the sky was indeed a great sphere. We were inside of kind of a bubble, is how they thought. Modern astronomers, of course, we know that's not true, but the idea still holds, and it's a very convenient way to describe the sky, which is probably why they naturally went to, hey, we're inside of this bubble, and there's all these holes poked in it, and there's this light shining through, and all of that. It may have been the way that people thought that the heavens were created. There's a lot of good history. If you're a history buff, history and astronomy and stuff, like, it's just very interesting stuff. There's science involved in it. It's one of the reasons I really love it so much. There's science involved in it. There's a little history. There's some personal stuff going on with it. There's like orientation stuff that kind of gets a little trippy. It's really fun to see these cool things that are out there in space. There's really a lot going on. So there's a few things that we need to kind of recognize as thinking of the sky as a sphere. For example, the sky appears to be rotating west around the Earth every 24 hours. The sun sets in the west, rises in the east, and it seems like rather than us moving, which is what's happening, it seems like the sky is moving. This sphere is moving around us, and we're kind of just standing still. Because you feel like you're standing still. You don't notice the movement of the Earth. But in fact, the Earth rotates east. So actually, it looks like the sky is moving west because the Earth is moving east. All right. The Earth's rotation produces the day and the night. From any location on Earth, you can see half of the celestial sphere. You can see half of it out to the horizon and up on a clear night or whatever. So that gives you kind of a piece. So you can see this whole half of the, if you were standing, like this guy standing up on, in the picture, it looks like he's in like North America, somewhere maybe, I don't know what area exactly, but North America, you could see the whole top of this thing, the whole equator. Actually, I don't know. Yeah, he's in North America. That's what it looks like, and you can see the equator rolling around there. Now, the equator has what's called the celestial equator, which is just if we took the equator around the Earth and we kind of just expanded it all the way out, it's just kind of an extension of our equator. So we call the celestial equator, which ends up being kind of how things rotate, because the Earth rotates around that celestial equator, around our equator, excuse me. Our equator, the Earth rotates around the center point and spins around, and that's what gives us day and night. And the celestial equator kind of stays in that same spot. Some other things to think about. Zenith is the point on the celestial sphere that's directly above your head. So that's what we call zenith. If you ever done three-dimensional anything, we have X, Y, and Z. Z is always the up part. So X here, Y this way, and Z up. So zenith, that's where the Z part comes from. Nadir is the point on the celestial sphere that's directly below your feet, and you cannot see because this is below the horizon. That's, it's underneath of you, but that's kind of the direction. We won't use that one too much because obviously you can't see things down here if you're up here. But we'll use the zenith and then all the cardinal directions. North and south celestial poles are directly above the Earth's north and south pole. I think I mentioned this in class the other day. If we look out from the North Pole here, so this is kind of tilted on its side, we see that the north pole here of the Earth points directly up to what we call the North Celestial Pole. All right, that's the point in the sky, and that's the North Star. If you that points directly toward Polaris, the North Star. And on the next slide, I'll show you how things kind of rotate around. Whoops, did not mean to do that. Let's go back. Here we go. So halfway between the celestial poles and celestial equator, I already talked about that. North, south, east, and west are also defined as the points on the horizon closest to the celestial poles for that. North and south, east and west are halfway between. So on the horizon closest to north. Notice how it's not exactly the same as celestial north. Celestial north is up in the sky where the North Pole points to. North for us would be on a flat curve like headed north. I'd go north, all right? That's when it's sitting in my house, that's that way. All right, south is this way, so east is that way, and west is this way. All right, and those are all kind of on the flat plane of the Earth. All right, and they work like that. So they're different than the North Celestial Pole, if that makes sense. Hopefully. The celestial equator always meets. That's a good point to point out. The celestial equator always meets east and west here on the horizon. So on the horizon, the east and west part, this will be very important considering the movement of planets and things like that. We've kind of mentioned that before, but we'll get there. So now we go into if you kind of get an idea of how this thing's laid out above us, we'll get to the sky around you and how the sky trails around. If you look, if you're looking north at the North Celestial Pole or the North Star here up to the top, everything's going to move around that. All right, the Big Dipper here, the Little Dipper is connected to it, and it'll kind of circle around. All right, and if you're looking north, it's going to move that direction. All right, so to the, I guess that would be, that's counterclockwise, right? Clock runs the other way. Yeah, so counterclockwise around the North Star, everything will move around that way. The one to kind of look out for is the orientation of the Little Dipper, and then the Big Dipper does a big wide sweep around, depending on the time of year or whatever. So that's how that happens. If you're looking east, all right, if you look directly east, things rise up straight out of there and go straight up, following that that curve that you saw before, following this curve. If you see east, see how it just comes straight up from there. Down in the west, if we have that one on the next spot, looking south, they kind of curve around there. If I look south, all right, look south is the same as looking north, but we can't see the south celestial pole. So it's not, south celestial pole's going to be down here off of the kind of the screen, or not off the screen, but off the you can't see it over the horizon, but you can see what's happening. It's the same idea. So these things that are close to the horizon will come up, and then they'll come right back down. So it changes your viewpoint of whichever direction you're moving, which way the stars move. But if you think of everything as a sphere or a big basketball that you're inside of, moving around, and the endpoints don't change, just like the Earth, you can kind of start to figure out how these things move. All right, this is from the northern hemisphere, obviously. You'd have the same idea from the southern hemisphere, just changed all those directions to south, west, and north here. So astronomers that use the idea of and measure distances as angles. They use angular distance to measure distances between objects. So what angle sweeps out from the looking at the star? They're expressed in angular units like degrees, arc minutes, arc seconds. They're also used to measure the angular diameter of an object, so how big something is in the sky, again by an angle. And what that angle is it's the angle that your eye makes from one object to the next object. And because it's a curve, again, we're talking about a sphere, so we're talking about angles, just like we talk about on the Earth, like latitude and longitude. Those are all measured from the center of the Earth out to the edge, along that curve, the sphere, like the Earth is. Same thing here, from us standing on the surface out to any star and to another star, sweeps out an angle. All right. If you can imagine two lines, one going to each object, the angular distance between the two objects is the angle that, right here in between. The sun and the moon have about the same angular diameter, which is very interesting. They're about a half a degree, so they're basically the same size. Even though the sun is super bright and may look bigger, what's it called? Moon is the same size, about half a degree. We'll get into more of the angles and stuff a little bit later when we need to use them to measure stuff. But that's how things are measured in the sky as well. What you see depends on where you are. So if you're at the North Pole and you're looking straight up at latitude of 90 degrees, you'll see kind of this celestial sphere looking like this. Everything will move around you at the top, which is very interesting. So if you're ever super far north, that North Star continues to move a little higher in the sky, and everything starts to spin around like this. It's kind of crazy. All right. The further you are down at a latitude of 60 degrees, the North Celestial Pole is kind of drops down a little bit. Once you get to about 30 degrees, which is going to be 30 degrees latitude, maybe like, I don't know, further south, like maybe Georgia. Once you get to Georgia, be at 30 degrees, or maybe even Florida, the North Celestial Pole is even further down. So what you can see in the Earth, people in Australia, they never see the Big Dipper. They never see the Little Dipper. They never see the North Star because it's on the other side of the Earth, which is kind of crazy. But you can see Alpha Centauri, which is just barely visible from above the southern horizon in Miami. So if you go to Miami, you can start to see it above the southern horizon. So you can't see everything from everywhere on the globe. We are in one single locked rotation. You can't see everything all the time. The stars do not just move all around us. They are in one spot and we are in one spot, and us just turning is what it sees. It's like as if you were sitting in a chair like I am, and all you could do is just spin around. Okay? I'm never going to see, my eyes are up here, I'm never going to see kind of what's underneath the floor because I don't rotate that way. All right. So if you were on the top of the Earth here at the North Pole and you started to walk around, you would start to see more and more and more of the sky, a different area of the sky, but you'd also be leaving behind part of the sky. If you walked across the Earth's equator, the celestial equator would pass right through your zenith, and as you continue to walk around, you would see everything. So if you could walk around the equator, you would get to see the whole entire sky as you walked all the way around. All right, so that's pretty cool. So it does depend on where you what you see on where you are. More of that. There's if you were on the equator as you were walking around, as you can see, you'd see everything from the equator as you go, and south celestial pole as you walk south. Same idea. So it depends on where you are on the globe as to what part of the sky you can see, and it doesn't really change. There are some things that will pop up with the seasons because of the way that we move around the sun, but most of it is the same throughout the year, the majority. This thing called circumpolar constellations, this is what we call the constellations like the Big Dipper and the Little Dipper that kind of rotate around the pole. So circumpolar, they make a circle around the pole, the North Pole, particularly like Polaris, and Ursa Major and Ursa Minor, the Little Dipper, Big Dipper, they circle around. All right, it seems like the sky is rotating this way. Perseus is in there, Cassiopeia, Cephas, those are all kind of circumpolar, what we call circumpolar constellations. They all rotate around, all right, and they're always visible. That's the key point. So they're always visible. You can always see the North Star, obviously if it's clear enough and stuff. But if you can see the stars, you can see the Little Dipper and the Big Dipper all the time in our area, including these other ones, Cassiopeia, Perseus, and so on. They kind of rotate right around there. So some cool things to look out for. How do we know what's going on with this? This is what we call a scientific model, and we break down scientific models. They are how nature works. These are models of our conception of how things work. Scientific model does not have to be true. Celestial sphere is a great example of this. There's no sphere on which these objects are attached, but using it gives us a framework for how to take in the location and apparent motion of these celestial objects. It's very easy for us to understand. We know what a sphere is or what a ball is, and we know how if we turned it, we can kind of get that concept, right? The ball and stick DNA model is kind of the same thing. The balls on this model represent atoms of the molecules, and the sticks represent the chemical bonds. These models can be simplifications of complex aspects of nature, like DNA and like the stars. It's a way to let people think about the phenomenon or mechanism in nature, but it doesn't need every single accurate detail. There's lots missing from both. They have their limitations, and it's important to keep those limitations in mind. So for us, they don't tell us, the celestial sphere model doesn't tell us the distance from Earth. I mentioned that earlier. It doesn't tell us that certain stars are closer to the Earth and certain stars are further away. It just gives us a way to lay things out on a map. This DNA doesn't tell us, model doesn't tell us things as well. So a discussion question: are the stars in the night sky during the day? Are stars in the sky during the daytime as well as night? Take a moment to think about that question. Now that you've had a moment to think about that, the stars don't go anywhere. I mentioned it in our class the other day, but the sun, the light from the sun is so powerful and scatters in the moisture in the atmosphere, and that's why our sky looks blue. So it gives us that blue color, and we can't really see through it. Plus, the sun is super bright. If you go out on a night of a full moon, which is coming up here, I think on Thursday night, the 1st, you'll go out during the full moon. You'll see the full moon up in the sky. It's going to be very hard to see other stars, and the full moon is not nearly as bright as the sun. So if we rarely see the stars during the day, but they are all around us. Sometimes during the day you can see the moon. Sometimes during the day you can see, and during the early morning hours when it's starting to be daylight, you can see things like Venus and Mercury. I used to see them all the time driving into the school because I drive south, and most of us probably do if we're going to school. We're headed toward the school south. And you can see, as you look toward the south, you can see, sometimes you can see Venus and Mercury like kind of peeking up to the south. So the bright light obscures the dimmer stars. You can't really see them from the bright light from the sun. But also, like, the sky turns blue because of the scattering of light in the atmosphere. All right, I think I want to end it there. I'm going to have to do a third part to this video. I don't want to make it too long, so we'll stop there and we'll get back to it soon.